Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Draw the influence lines for the vertical reactions at the supports and the shear and bending moment at point C of the two-span continuous beam shown below. E is constant. Plot ordinates every 3-meter intervals. Also compute the maximum value of AY and V sub C or shear at C due to the combined effects of the live load of 15 kilonewtons per meter and dead load of 2 kilonewtons per meter. So here is the given beam, continuous beam. Take note that portion AD has moment of inertia 2I, DG has moment of inertia just 1I. So we have here the primary beam subjected to unit load at D. So the deflection here is in particular FDD. The, the deflection at point D due to the unit load at D. But in general here, if we remove this as if we choose this as the redundant, by the way, the beam is indeterminate externally to the first degree, so that we select dy as our redundant reaction. So if we remove this, the beam will deflect and it becomes determinate. The corresponding deflection here is supposedly the Fd due to the unit load at P, but by Maxwell's law on reciprocal deflection, we call the deflection at each point selected every 3 meters as in general F, for instance at B, F, B, P, but it is also equal to F, PB. So take note of that principle. So that's why we call this FDD. And for FDDR, primary beam subjected to the redundant, by the way, if we solve for AY due to this unit load at D here, this is 0.4 and this is 0.6. So just do the static summation moment at G, you can solve 0.4 for AY. Summation moments about A, you can solve 0.6 for GY. Then this is the primary beam loaded with the redundant dy. So it is the same as this except that the deflection is denoted by FDDR and the deflection would be positive for this case. So in general, dy, ordinates for dy would be equal to F dp negative F dp over FDDR. So dy is negative FPD or FDP over FDDR. Then FDDR is the negative of FDD because this loading situation is the same except that FDDR is positive when the unit load is acting at D. The position of the unit load at D where dy is our chosen redundant force or redundant reaction. So by double integration, I present double integration here for portion AD. So E times 2I, because moment of inertia is 2I, of FAD double prime equals zero point 0.4. So zero point 0.4 of x, imagine this is our sectioning. The equation, moment equation for the portion AD, the distance is x from A, so zero point 0.4 times x. Before we integrate, we divide everything by 2, so EIF double prime AD is zero point 0.2 of x. Integrating once, EIF prime AD is zero point 0.1 x squared plus C sub 1. So there is slope at A, but there's no deflection at A, so there is no C sub 2. Integrating further, EIF AD is equal to x cubed over 30 plus C sub 1x. So as I said, there's no C sub 2. Then for dg, EIF double prime dg is equal to 0.4 of x minus 1 times quantity x minus 9. This distance is x minus 9. We look at this figure. Integrating EI f double prime dg is zero point 0.2 of x squared minus 1 half of x minus 9 square plus c sub 3. So there is c sub 3 but there's no c sub 4. Sorry, there is c sub 4 because it is dg. So that c sub 4 is the another constant representing the deflection at the origin when, which is d for this portion of the segment. So EI FDG is equal to 1 over 15 x cubed minus 1 6 quantity x minus 9 cubed plus c sub 3x plus c sub 4. So beginning with this equation, when x is 15 meters, applicable to this, so from d to g, y is, or FDG is 0. So 0 equals 1 over 15 of 15 cubed minus 1 over 6 of 15 minus 9 is 6 cubed plus c sub 3 times 15 plus c sub 4. Simplifying this equation, 15 c sub 3 plus c sub 4 equals 6 square minus 15 square. So 15 c sub 3 plus c sub 4 equals negative 189. Call that equation A. Then the slope at D, just to the left and just to the right, will be the same because the beam is solid and continuous. So that means the slope is the same. So this represents slope just to the left of D. This represents slope just to the right of D. They are equal when x is 9. So 0.1 times 9 square plus c sub 1 equals 0.2 times 9 square. This is 0, so plus c sub 3. C sub 1 minus C sub 3 is 0.2 times 9 square minus 0.1 times 9 square, and that is 8.1. Call that equation B. Finally, the deflection just to the left and just to the right of D will be the same. So we equate this and this equation when x is 9. Take note that this is 0 when x is 9. So 9 cubed over 30 plus C sub 1 times 9 equals 1 over 15 times 9 cubed plus c sub 3 times 9 plus c sub 4. Simplifying, 9 c sub 1 minus 9 c sub 3 minus c sub 4 is 9 cubed over 15 minus 9 cubed over 30, and that is 24.3. Solving equations A, B, and C simultaneously, then we have c sub 1 equals negative 7.74. C sub 3 is equal to negative 15.84, and C sub 4 rather is 48.6. Then EI FDD when x is 9, so this is the simpler equation than this equation here, but this is also applicable. So 9 cubed over 30 plus negative 7.74 times 9. So that is the value of EI FDD. So FDD therefore is equal to negative 45.36 over EI. Since FDDR is the negative of FDD, so FDDR is positive 45.36 over EI. So therefore, the formula for dy would be from 0 to 9 would be this. That's for dy. Then divided by FDDR. So this expression here. So dy is negative of quantity x cubed over 30 minus 7.74x over 45.36 from 0 less than equal to x less than equal to 9. Then for dy from 9 to 15, let's have it on the next slide. So dy from c to 9 is negative of quantity x cubed over 30 minus 7.74x over 45.36 from 0 less than equal to x less than equal to 9 meters. Then from D to G, then it is EI FDG is equal to 1 over 15 x cubed minus 1 over 6 x minus 9 cubed. then minus c sub 3, which is negative 15.84 times x, plus c sub 4, which is 48.6. So divided by FDDR, so FDG is equal to negative of quantity x cubed over 15 minus 1/6 of x minus 9 cubed minus 15.84 of x plus 48.6 divided by 45.36. This is from 9 to 15 meters. We can now plot the ordinates. So this is AY, DY, and GY. If we sum up moments about G, we can derive an expression for AY in terms of dy. So AY times 15 plus dy times 9 equals 1 times 15 minus x. So divide everything by 15, AY equals 1 over 15 times 15 minus x minus 0.6 over 15 is 0.4. So 0.4 of dy. This is for 0 less than equal to x less than equal to 15. But if we express it in terms of dy, remember that dy is divided into two parts, from 0 to 9 and the other one from 9 to 15. But anyway, after we solve for dy, we just substitute the value of x, we can solve for ay. Then summation forces y, considering the whole system, ay plus dy plus gy equals 1. Therefore, gy is 1 minus ay minus dy for 0 less than equal to x less than equal to 15. So we now tabulate values of x, then dy, ay, then gy. dy, ay, then gy. When x is 0, remember this is the expression for dy from 0 to 9, so 0. 0 cubed over 30 minus 7.74 times 0, so 0 over 45.36, 0, so 0. Then ay, which is given by this expression, 1 over 15 times 15 minus 0, so 1 minus 0.4 of 0, so 1. Ay is 1. Then gy, 1 minus 1 minus 0 is 0. When x is 3, 3 cubed over 30 minus 7.74 times 3 over 45.36, then the negative of that value. So it will give us 31 over 63. Then ay is 15 minus 3, so 12 over 15, 0.8. 0.8 minus 0.4 of 31 over 63. 0.8 minus 0.4 of 31 over 63, it will give us 38 over 63. Then gy is 1 minus 31 over 63, or minus 38 over 63 minus 31 over 63. So gy is negative 2 over 21. For x equals 6, then there are two values, 6 left and 6 right. So 6 left. So since this is 0 less than equal to x less than equal to 9, so it is applicable here. Negative of quantity 6 cubed over 30 minus 7.74 times 6 over 45.36, 109 over 126, so it is also 109 over 126, 6 just to the right of 6. Then ay is 15 minus 6 is 9 over 15.6. 0.6 minus 0.4 of 109 over 126. So ay would be 16 over 63 for just to the left and just to the right of 6. Then gy is 1 minus 16 over 63 minus 109 over 126. So gy is negative 5 over 42, just to the left and just to the right of 6. Next is when x is 9, dy is 9 cubed over 30, negative of quantity 9 cubed over 30 minus 7.74 times 9 over 45 over 36. It's equal to 1. So ax is 15 minus 9 is 6 over 15.4. 0.4 minus 0.4 of 1, so 0. Ay is 0. Then gy is 1 minus 0 minus 1. so it is also 0. When x is 12, so this is no longer the applicable formula. So this is the applicable formula. Negative of quantity 12 cube over 15 minus 1 over 6 times 3 cube minus 15.84 times 12 plus 48.6 over 45.36. dy is 19 over 28. Ay is 15 minus 12, 3 over 15, so 0.2. 0.2 minus 0.4 of 19 over 28. Ay is negative 1 over 14. Then gy is 1 minus negative 1 over 14 minus 19 over 28. So gy is 11 over 28. Finally, when x is 15, dy is 15 cube over 15 minus 1/6 of 6 cube minus 15.84 times 15 plus 48.6 over 45.36. Then the negative of that value is 0. Ay is also 0 because 15 minus 15 is 0 over 15, 0 minus 0.4 of 0, so 0. Then gy is 1 minus 0 minus 0 is 1. So we can now plot dy, ay, and gy. So for dy, it begins with 0, then 31 over 63 when x is 3. X is 609 over 126. X is 9, 1. Then x is 12, 19 over 28. X is 15, 0. This is the influence line for Ay in kilonewtons per kilonewtons. It begins with 1, then 38 over 63, 16 over 63, 0 when x is 9, negative 1 over 14 when x is 12, 0 when x is 15. Then gy, it begins with 0, negative 2 over 21, negative 5 over 42, 0, 11 over 28, 1. So that's it. Then for the maximum value of Ay, so let's have it on the next slide. So we have Ay here. Let's draw free body diagram from A to C, and the unit load will be up to 6 only. So this is the positive shear at C, positive moment at C. So for maximum Ay, we sum up, maximum Ay, we need formula for V sub C also. So V sub C is Ay minus 1 for 0 less than equal to x less than equal to 6 meters. Beyond 6 meters, the unit load is no longer part of the free body diagram. So if we remove this, V sub C equals Ay for 6 meters less than x less than 15 meters. So M sub C, summation moment about C equals 0, M sub C plus 1 times 6 minus x equals Ay times 6. Therefore, M sub C is 6 times Ay, then minus 1 times 6 minus x for 0 less than equal to x less than equal to 6. Then beyond that, the unit load is no longer part of the free body diagram. So if we remove this, M sub C is 6Ay for 6 meters less than equal to x less than equal to 15 meters. First, for maximum Ay, remember that we have found Ay, the ordinates of Ay in the preceding slides. So we have 0, 1, 0, so we will include M sub C if we want. So when x is 3, Ay was 38 over 63. So V sub C is 38 over 63 minus 1. It's negative 25 over 63. Then when x is 6, just to the left and just to the right. Just to the left, this is the formula. Ay was 16 over 63. So 16 over 63 minus 1 is negative 47 over 63, just to the left. Then just to the right, this is now the applicable expression. So that's why just to the right, it's also 16 over 63 for V sub C. Then when x is 9, Ay was 0. So v sub c is 0 also. Then when x is 12, ay was negative 1 over 14. So v sub c is also negative 1 over 14. When x is 15, ay was 0. So v sub c is also 0. So if we include m sub c, summation moment, so this is the applicable equation, 6 times 1 when x is 0 minus 6 is 0. When x is 3, 6 times 38 over 63 minus 1 times 6 minus 3, so minus 3. M sub c is 13 over 21. When x is just to the left of 6, so this is the applicable formula. But when x is 6 less than equal to 6, because this is moment, so this is now the applicable formula. So 6 times 16 over 63, that would be 32 over 21. So just to the right, since it is also 6ay, so it is also 32 over 21. Then when x is 9, ay is 0, 6 times 0, so m sub c is 0. When x is 12, ay is negative 1 over 14 times 6, so negative 3 over 7. When x is 15, ay is 0, so m sub c is also 0. Then to plot v sub c and m sub c. So we have here for ay, I don't need to discuss this. It was drawn in the preceding slides also. Just for v sub c, it begins with 0, then negative 25 over 63, negative 47 over 63. Just to the right, it becomes 16.63, then 0. When x is 9, negative 1 over 14, then 0. So you can have the shortcut by qualitative influence line technique by Muller-Breslau. So we replace this by a roller which can resist moment but cannot resist shear. So if we push this downward, it will look like this graph. Then on the just to the right, we push it upward, it will look like that. So that's why it looks like this graph here, just to verify. So ay is equal to negative 1 over 15 times 15 minus x minus 0.4 of dy. For 0 meter less than equal to x less than equal to 15. But remember, dy has two parts. This is the first part. So 1 minus x over 15, then minus 0.4 of dy negative of quantity x cubed over 30 minus 7.74x over 45.36. So if we simplify and combine like terms, negative of negative 7.74 x over 45.36 is negative. Then minus 1 over 15. So ay is 1 minus 17 over 126x. Then negative of x cubed over 30 over 45.36 times negative 0.4, it is positive. So it is x cubed over 3402. This is for 0 meters less than equal to x less than equal to 9 meters. So take note that ay is 1 minus 17 over 126x plus x cubed over 3402 from 0 to 9. Then 9 to 15, so ay is 1 minus x over 15 minus 0.4 of negative quantity x cubed over 15 minus 1 over 6x minus 9 cubed minus 15.84x plus 48.6 over 45.36. So let's simplify this on the next slide. So for the expression for ay from 9 meters to 15 meters, so ay is 1 minus x over 15 minus 0.4 of dy, and dy is negative quantity x over 15 minus 16x minus 9 cubed minus 15.84x plus 48.6 over 45.36. So combining like terms for the constant, we have a constant here, negative of 48.6, so divide by 45.36, that's negative, times negative zero point 0.4, it becomes positive, plus 1, so AY is 10 over 7. Then for x, we have negative 1 over 15x here. We have negative of negative 15.84, x over 45.36, that's positive, times negative zero point 0.4, so that's negative. Then minus 1 over 15, the net result is negative 13 over 63x. For this cubic expression, negative of x cubed over 15 divided by 45.36 is negative, times negative zero point 0.4, so positive, and it is x cubed over 1708. Then from 9 to 15, that's why this is for 9 to 15, so we include negative of negative 16 is positive 16 of x minus 9 cubed, divided by 45.36, so positive, times negative zero point 0.4, so negative 5 over 3402 of quantity x minus 9 cubed for 9 meters less than equal to x less than equal to 15 meters. So AY is 1 minus 17 over 126x plus x cubed over 3402 for 0 meters less than equal to x less than equal to 9 from the preceding slides. So we can now have this, the value of AY max by integration. So take note that AY is positive from 0 to 9 and it is negative from 0 to 8, and AY is positive. So the live load should be placed from 0 to 9, which is 15 kilonewtons per meter, but the dead load is covering the entire span, so it also covering this span here. So therefore, for A to D, the load would be 15 plus 2, so 17 kilonewtons per meter. And from D to G, the load would be just the dead load of 2 kilonewton per meter. So AY max by using the equation is 17. Then the area under this curve, integral of quantity from 0 to 9, 0 to 9, the equation of this curve is this one, 1 minus 17 over 126x plus x cubed over 3402, then dx. So the value of this by integration is then plus 2. This one is due to dead load only, uniform. The equation is 10 over 7 minus 13 over 36x plus x cubed over 1701 minus 5 times quantity x minus 9 cubed over 3402. Then times the uniform load 2, and this is the area. The value of the first integral is 68.3034. The value of the second integral is negative 0.57143. Adding, AY max is equal to 67.732 kilonewtons. That is if we base it on the equation, and by the definition it is equal to uniform load, then the area under the load, under the curve. But if we analyze this by three moment equations and with the aid of the technique by Muller-Bislau, wherein we have to load this by live load and dead load, and in this part where the area is negative is just the dead load, then we can also analyze this by three moment equation, computing the moment at D first. Moments at A and G are all zeros, so remember the three moment equation, moment at A times L1, which is 9 over I, but moment at A is 0, so don't mind, plus 2 times moment at D times the quantity length of AD over I, which is 2, plus length of DG, which is 6 over 1, because the moment of inertia is 1, plus moment at G, which is 0 times 6, so it's just 0, plus the value of 6A1A over L1 is W L cubed, so 9 cubed over 4, then I is 2, so times 2. The value of 6a2b over L2i2 is 2 times 6 cube over 4 times 1, then equals 0 because there is no settlements or support movements. So moment at A0 to MD quantity 9 over 2 plus 6 over 1 plus MG which is 0 plus 17 9 cube over 4 times 2 I is 2 plus 2 6 cube over 4 times 1 equals 0. So simplifying, we can now solve MD moment at D is equal to negative 78.911 kilonewton meter. So let's apply it here. It is clockwise because the positive sense at the left side is clockwise positive for moment, then counterclockwise at D, so that it will have a smiley figure. But since this is negative, so it means it is clockwise as shown. So this is AY, which corresponds to AY max. And we have moment here, we have shear at D, just to don't mind because our equation is summation of moment at about D, so that we consider AD, we can solve for AY. AY is the corresponding AY max. So AY max or AY times 9 plus this moment, which is 78.911, then equals moment of the load 17 times 9. Moment arm is 9 over 2 or 4.5. Again, summation moment D equals 0. So AY or AY max times 9 plus 78.911 equals 17 times 9 times moment arm 4.5. From there, we can solve AY, which is AY max equals 67.732 kilonewtons, which is the same as that. For maximum shear at C, let's have that on the next slide. So for shear at C, remember shear at C is AY minus 1 for 0 less than equal to X less than equal to 6 meters. And remember that AY in terms of dy has two expressions. 1 minus 17 over 126x. Then I forgot the other term. You just pause the video, then look at the expression. So it is negative minus 1, so therefore it is negative 17x over 126 plus x cubed over 3402. Because from 0 less than equal to x less than equal to 9, AY was 1 minus 17x over 126, then plus x cubed over 3402. There was 1 here in the first term. Since here at C from 0 to 6 is given by this expression, so from 0 to 6 it is, we remove positive 1 and negative 1, so negative 17x over 126 plus x cubed over 3402. Therefore, for in particular 6 to 9, since 6 to 15, V sub C is AY, but from 6 to 9, we have 1 here, but from 9 to 15, the expression is different because AY has term 1/6 of x minus 9 cube minus 15.84x plus 48.6. The first term was, I think, x cubed over 15. So V sub C is 1 minus 17x over 126 plus x cubed over 3402. This is for 0 up to 9. Therefore, in particular, for 6 and 9, this is the applicable equation of this curve for shears at C. 6 to 9. Then 9 to 15 would be V sub C is 7 integral of from 0 to 6. So negative 17x, the area here is expected negative. By the way, the maximum shear is negative. There are two regions where shear is negative. There's only one that is positive. So 17, 0 to 6, take note, this is the expression for V sub C. Negative 17x over 126 plus x cubed over 3402 dx. That's the area under the curve from 0 to 6. Then this is from 6 to 9. V sub C is from 6 to 9, AY minus 1, because AY is equal to this expression from 0 to 9. So from 6 to 9, therefore, this is still the applicable interval. So we copy that expression for V sub C, but the limit 6 to 9. And this portion is loaded with just the dead load. This part would be live load and dead load, live load and dead load. Remember, the dead load is 2, the live load is 15, so 2 plus 15 is 17. Then here, just the dead load only. We do not load this with live load because it is positive. If you look at the figure, the maximum shear is negative. So this is the expression from 6 to 9, and the W is just the dead load 2. This is dead load and live load for 0 to 6. Then from 9 to 15 rather, the expression is different. It was 10 over 7, 17, 9 to 15, 10 over 7 minus 13x over 63 plus x cube over 1701, then minus 5x minus 9 cube over 3402. And you just look at the expression for AY from 9 to 15. So take note, this is from 9 to 15. AY in the previous slides. So using your calculator, the value of this integral, this is expected negative. We have negative area. Negative 119 over 3, the exact value. The second term is expected positive. The integral times 2 is 59 over 84, so it's positive, it's correct. Then the area of the value of the third integral times 17 is negative because the area is negative here. Negative 34 over 7. So combining negative 119 over 3 plus 59 over 84 minus 34 over 7, the value is V sub C max is negative 43.821 kilonewtons. Now, how do we solve this? By three-moment equation. So we first compute the moment at C. Take note that we load from 0 to 6, from A to C with dead load and live load, which is 17 kilonewton per meter. From C to D, we load it with just 2 kilonewton per meter, and from D to G, we load it with 17 kilonewton per meter again. So that's the loading arrangement or load pattern. Dead load and live load, dead load and live load. This is just dead load. So let's compute for moment at D first by three-moment equation. Take note, moments at A and G are all zeros. Then 0 plus 2 md, quantity 9 over 2 plus 6 over 1. mg is 0 plus integral of 17 dx. A is x, b PAL. This is differential P. This is A. So our strip, the distance from left is x. The same as the strip here, the distance from left is x. But the limits of x for this, so the formula is differential P A over L times I, which is 2, quantity L square minus A square. So 17 dx differential P. X is A, the distance of the centroid of strip from A is x, divided by L, and moment of inertia is 2. Then quantity L square minus A square, A is x. Then for the second 2 dx, A is x. Then divided by L times I, which is 2 also for portion CD. Then L square minus x square. However, the limits for the second integral is from 6 to 9, 6 meters to 9. Then for the last, we don't need to integrate because there's a direct formula for that. That's 17 6 cube over 4, WL cube over 4. Then equals 0 because there are no support settlements. So the value of this integral is 1071. This integral is 56.25, and 17 6 cube over 4 is equal to 918. 1071 plus 56.25 plus 918 to the right is negative. divided by 21. The coefficient of MD is 21. So MD is negative 97.393. So since it is negative, it should be clockwise, just to the left of D, and it is 97.393. We first compute for AY, then after we solve for AY, we apply the moment and shear at this section C here. The positive shear is going down, then we sum up forces vertical to derive shear at C maximum. So this is the moment at C, then shear at C maximum. Call that AY. So AY times 9 plus 37.393 equals moment of 2 kilonewton load. 2 kilonewton per meter load is 2 times 3 moment arm 1.5 plus the moment of this load with respect to D is 17 times 6. This is the centroid. The distance is 6 also. So AY is equal to 58.179 kilonewtons. Then let's now apply the shear at C, which is positive going down. Then summation forces vertical equals 0. So V sub C max is AY minus 17 times 6, the area of this load. So V sub C max is AY, which is 58.179 minus 17 times 6. So V sub C max is equal to negative 43.821, so which is the same as this integral. So in other words, since it is challenging to derive the expression for shear or moment at a point as compared to the technique by Muller-Breslau, after knowing where to place or to position the dead load and live load, or the dead load alone, then we just analyze the beam, continuous beam, by the 3 moment equations. Then after that, we draw free body diagrams involving the required function or redundant. Then we solve for that redundant by statics. So this is by statics, and this is by the equation of the curve in terms of x, but it is a challenging part, and you might forget, supposedly not, because the technique in deriving this equation is based on the deflection equations for due to the unit load positioned at the positioning of the selected redundant. In this case, there's only one redundant, so it's easier. Then after that, after we derive that, then we don't need this equation. But for me, it's easier if we just position the loads and analyze it by the available method, 3 moment equation or slope deflection equation, whichever is easier for you to apply. But for me, it's 3 moment equation, the better way. But you might forget this expression, so you have to derive this again, the value of 6A1A over L1I1 or 6A2B over L2I2. So you can derive using slope deflection equations, but the equation will be longer if we apply slope deflection equation. So depending on which method in analyzing continuous beams would you prefer, then apply it and you just load the position. So that's it, and I hope you were able to follow the solution of this problem.